Hello, my name is Jeremy, and I'll be presenting the paper Extend, Push, Pull, Smartphone Mediated Interaction in Spatial Augmented Reality via Intuitive Mode Switching. This is part of the work I'm doing with Akar Gupta at the Facebook Reality Labs and Daniel Vogel at the University of Waterloo. Our smartphones have become critical to our day-to-day lives. Obviously, we use them for communication, but they are also becoming crucial to our entertainment and productivity needs. But all this content is currently constrained to the small screen on the phone, making it hard to get out and share with other people, or other collaborators that may be around the user. So we created an interaction technique that outlines a way to get content out of the phone into the real world, but also pull it back into the phone from the environment. We do this through an intuitive mode switching gesture that mimics our natural tendency to point at things. There is a significant amount of work that has explored the space of smartphone pointing and also around body interaction. Using a smartphone for pointing tasks have been explored by Myers et al., whose semantic snarfing technique motivated our approach to capture content on the phone. Siefter et al. Expanded on this through their exploration of smartphone interaction on a large display. And Lagner et al. Explored a hybrid pointing technique that can interpolate between a direct raycast and an orthogonal projection on a very large display. The space around the user's body has also been explored for purposes of interaction or to store virtual content. Yi et al. Used a PDA device to explore the hidden virtual content anchored around the user. And Li et al. Expanded on this by placing smartphone apps spatially around the user for the user to interact with and testing their memory. And Chen et al. Explored the interaction space in front of the user. By tracking their face, they were able to explore some interesting novel interactions. Our work expands on all of these by looking at the distance and orientation of the smartphone relative to the user's head. We then use this to create a method to delineate between a relaxed and extended pointing gesture that is used as the basis of our technique. One of the main issues we address is to provide a set of interactions that do not conflict with the existing ways we use our smartphones. So we developed 5 design goals that we follow to ensure our technique is intuitive, so that the transition between a native smartphone application and spatial content should be easy to discover and understand by the user. Conflict-free, the method should avoid conflicts with existing system-wide input. This includes things like bezel swipes or forced presses. All of these should not conflict with our technique. It should be comfortable. The method should avoid continuous or extraneous postures and provide a way for the user to be in a relaxed state while doing some interaction. It should also be one-handed, so all interaction should be doable with a single hand and not necessarily requiring a second one. It should also be eyes-free. The user shouldn't have to look directly at the smartphone during an interaction and be able to do it without any eye assistance. From this, we developed our interaction technique that splits smartphone interaction between 2 main modes. The first is mobile interaction mode that lets the user use the smartphone as they typically would normally. And the second is the spatial interaction mode that lets the user interact with spatial content through the techniques we outline in this paper. And these can be seen in the figure on the screen. We use the extend gesture to switch from a mobile interaction mode to the spatial interaction mode. This allows the user to switch between the modes fast and effortlessly by simply having them extend their arm away from their bodies. The user can then push content into that physical space around them by using a combination of the extend gesture and a screen flick. And this allows them to place content directly into the real world. Pulling content back into the phone is also possible by selecting content that is spatially present in the real world and then retracting the arm back to a relaxed state. An app will then pop open that is coupled with the virtual content and allow the user to manipulate different features that may be available. Rotation, scale, and translation can occur if the user is in the spatial interaction mode state. The user activates the RST through a long press and can then perform rotation, scale, and translation on the objects all at once, which will provide a fast and easy way to quickly manipulate the content in the space that the user is in. Crucially, when in RST, the user can relax their arm so they can bring it back in a relaxed state while they still perform the manipulation. This provides a comfortable posture as the user manipulates the content. All of these states, the extend, the push, and the pull, provide the basis of our interaction technique and allow us to explore the interaction set that is conflict-free and also while ensuring that our design goals are met. To validate the interaction techniques, we built a system to explore our design considerations. And you can see this here in the video, which shows 5 projectors with Vicon cameras that are used in our system. The projectors are calibrated using the Room Alive toolkit, and one-time calibration is used to synchronize the projectors with the Vicon system so that they share the same coordinate space. This allows us to place 2D content into the physical environment that will look perspectively correct from any viewing location in the environment, which is required if there's more than a single user happen to be within that environment. Altogether, the placement and manipulation of content can be accomplished by pushing the content into the physical space. And when the user is still in the extended mode, they can scale and translate it by performing gestures on the phone. And you can see this here in the video where the user places an image and then proceeds to adjust all the images through translation, scale, and rotation so that they look better on the wall. And spatially distributed content can be removed from the environment by extending the phone to enable the spatial interaction mode, pointing at the content, and then flicking down on the smartphone screen. Here you see the user removing photos that were previously placed in the environment. Rotation of the content can be performed by first selecting the content, and then moving the thumb left or right on the screen, which will then rotate the image either left or right. A scaling is accomplished by moving up and down on the screen while the content's selected. And you can see here in the video the user both scaling and rotating the image, and the scale is uniform along 2 dimensions of the image. Translation works by selecting an object when in the spatial interaction mode, and move the smartphone left or right in the space. The objects will automatically snap to the surfaces that they were relocated to, aligning with the surface normal of the object. And this makes it easy to quickly switch objects from, like, say, the wall to a box, or from a box to a table. Capturing content can provide additional interface for the fine manipulation and adjustments of the content in the environment, like adjusting the brightness of an image located spatially in the world. And here you see the user in the video selecting images and adjusting the brightness. And once they select the image, a widget pops up and they can adjust the brightness through a slider. We built 3 applications that use our interaction technique for content placement and manipulation. This includes a photo application, and this was seen in the previous examples, but also a weather application, which you can see right here in the video, and then finally a mapping application that allows users to search different maps and provide destinations. The Weather app lets the user place weather widgets in the physical space. These widgets can display relevant information, and the user can capture them to adjust their visual feel and look as well. like providing an ambient lighting that might represent what the real weather state outside might look like. Here in the video, you can see the user placing a widget and then also manipulating it to on the wall, and then capturing it, which you can see here, which provides a series of buttons that the user can use to adjust the look and feel of the content. And what's nice is that there's a one-to-one coupling between them, and so that you see the visual feedback right away. The Maps application lets the user place a map into the environment, and this can be used for like either collaboration or for viewing of multiple people. And you can see here that you can capture that map, and then you can change the destination on the map. So the user in the video is changing from San Francisco to a destination between London and Paris. So to enable the extend and retract states, we conducted a study to collect data from 12 users using our technique. We placed markers on the walls at precise angular offsets from 6 different locations that correlate with the sit, stand, supine postures in a near and far configuration. If you imagine the figure on the left like wrapping around the surface of a sphere, where the middle concentric circle fits at the sphere's equator, and the middle target, number 3, faces forward, then you get a rough idea on how those targets are mapped to the angular offsets that are present in the space. And this can be seen on the right side of the slide, where the yellow points indicate the target placements for a particular location. And the participant would then go through each configuration pair and point at particular targets that are displayed on the screen. We would then collect data points when the user is in the relaxed state, reading from the screen, and then in the extended state when they point at the target. And then across all the participants and configurations, we collected 5,328 data points that were used for our classification. The collected data is visualized in this slide here. You can see each of the 6 configuration pairs, and then also you can see the convex hulls of the points. And this really shows the how diverse the point clouds are across each configuration pair. With the collected data, we wanted to see how well we could delineate the extend relax states with a simple radius from the user. We utilized a spheres fitting algorithm to get the optimal radius based on the data we collected. This radius turned out to be 53.85 centimeters away from the user's head, based on the data that we collected. Anything inside of this radius would be considered the relaxed state, and anything outside of this would be considered the extend state. So it would have been a simple classification, binary classification. However, this only was accurate for 83% of the data, which was not sufficient enough for us in all of our use cases that we wanted to explore. So in order to further explore the data and to see how we can improve on the simple radius delineation model of the extend relaxed state classification, we trained a random forest classifier on the data we collected and found that overall we could greatly increase the accuracy of the classification to a general accuracy of 96%. With the sit far having the highest accuracy at 99%, and the supine near at the lowest accuracy at 93%, particularly for the per user height variant of our classifier. More details of this and how it works is in the paper, and I encourage you to go read the paper to get into the details on the classifier. We then recruited 6 participants in a pilot study. Each of them was asked to perform a series of tasks using our interaction technique we outlined earlier. This included manipulation of images and placement of content. We found that participants thought that the interaction techniques were easy to use overall, but some had difficulty with the technique when lying down. This was due to the size of the phone, which made it sometimes difficult to hold for that particular posture. This can be seen in the figure where the physical demand for supine is much larger than the other two postures. That's the end of the presentation. More details are in the paper, and feel free to contact me directly if you have any questions. Thanks.